Alrighty, let's get started. We've been having a wonderful time this week with workshop, bringing together some mathematicians and physicists, and on the general topic of trying to understand the thorny issues of infrared divergences for a physicist using fascinating ideas in tropical geometry. There's been many aspects of the interaction with tropical geometry in this kind of physics roughly over the past number of years, and we're really delighted today to have Nishi here telling us about some new aspects of it that he's been working on, and so please take it away, Nishi.
Thank you very much, and yeah, thank you for the opportunity to speak here today, and also thank you for organizing this fantastic workshop during the week. I had so many interesting discussions, and all the talks were fantastic, so thanks again for that. I'm going to talk about something which is slightly more mathematical. So this is the dark matter problem. So I'm sorry about the clickbait title with the dark matter in the modular space of curves. And this dark matter problem has a tropical solution. And I'm also going to explain in this talk why it's only a partial solution, this tropical way to approach this dark matter problem. So during this talk, so don't be scared, I'm going to explain like what all these different objects and things mean. So I'm going to explain the actual dark matter, what it is, the modular space of curves, the tropical modular space of curves, and why it's only a partial solution. And I'm going to try to include also analogies to physics, and especially to like the tropical geometric treatments that we saw during the week. And I hope you recognize many relationships and parallels in the story. So the main player is the modular space of curves. It's a very important object in algebraic geometry. It has been studied like for more than 120 years, starting with the work of Riemann. Physically, it also has a nice interpretation as the space of all two-dimensional quantum gravities. So it's the configuration space in a way of two-dimensional quantum gravity. So in precise terms, mg can be thought of as the space of all hyperbolic metrics on a surface which is connected, orientable, and of genus G up to isometric diffeomorphisms. So we take a surface of genus G which is orientable and connected, and we want to consider like all possible ways to put some metric, some hyperbolic metric on the surface, and we are not interested in diffeomorphics metrics that are equivalent by some diffeomorphisms. You can think of this modular space really as a space in which each point is given by some hyperbolic surface. So we can embed it in space by requiring that we only want constant curvature. So we can really think of this modular space as a space of these kind of surfaces that we can realize geometrically. So this is a point in this M2 in the modular space of genus 2, the double bagel. So the surface with two holes. You can move around in the space and deform like different handles in the space. So you get different deformations and metric changes in the surface. There are many ways to do this. So you can stretch out one of these handles here on the side. And in general, like you have this whole space of different opportunities to go to. What's important for this talk is that mg is not a compact space. So there are sequences of these kind of surfaces that don't converge to a point in the space. And I have a very nice low budget animation of this phenomenon. So you can stretch out a tube on one side here of the double bagel and get a very long and thin tube, for instance, like this. And then you might think, yeah, we can go to the boundary and we get something which is pinched at this point. So we get a a tube which actually has 0 length. So because of the hyperbolic metric, what we see is that if we have like a tube that is very thin, so that it has a small geodesic, then it also has to be very long. But we might expect that we can go to the boundary. So this is also very interesting to consider these boundary points. But in this case, they are not included in the space. So we don't want singular points in the modular space. All right, so we only have these smooth curves in the modular space. But here's already the first analogy. So you can think of these long and thin tubes that pop up on the boundary as some kind of infrared divergences in this modular space of curves. And I think also in string theory, I'm not quite sure, but one can also give like some infrared interpretation of these boundaries of the modular space and as infrared divergences. I see. So it's as much. Thank you. So what's of interest here is the topology of this modular space of genus G curves, and yeah. So we want to use this information, like on this boundary especially, to learn something about the topology. Yeah. So this is a physical. This is a more mathematical motivation. And to understand what this, why this is interesting is this picture that I had before is a bit misleading, because in general there are many higher dimensional holes in these modular spaces. So you can think of this as higher dimensional holes that are scattered around it. So before that, I kind of suggested that this is just a ball where you can move around, but actually you can move around like complicated higher dimensional holes in this modular space. Not in M2 actually, but in the higher dimensional versions you can do that. So it's of course, it has a long tradition to use physical tools to study this modular space. So that maybe started with the work of people around Itzigsen, perhaps, I don't know, but of course they were in the 90s, starting with Witten, and there were many important results on the topology of this modular space and its generalizations. And then there are also like more different things connected to matrix and models and random matrices by Francesco, Ginsberg, and Justine. Just to mention like some older work. So one thing in the topology to look into is the cohomology of the space. And so this is only rational cohomology. I'm only talking about rational cohomology here. And so we want to look into HK of MG with rational coefficients. And these are the rational cohomology groups. So if you want, you can think of them as differential forms on this modular space that are closed and not exact. But also roughly the dimension of the kth homology group, cohomology group, it gives us the number of k-dimensional holes in this modular space. So this cohomology is a measure of the k-dimensional holes in the space. Right. So what's known about this cohomology of this modular space? Unfortunately, not very much. So the first thing that is known is that the space itself is a 6G minus 6 dimensional space. That was already figured out by Riemann. So this is 6G minus 6 real dimensional. But from the perspective of topology, the space pretends to be a 6G minus 5 dimensional space. But it turns out that the cohomology also vanishes in the top degree. So from the point of view of cohomology, the maximal dimension is 6G minus 6, at least from the point of view of rational homology. And this was proven by Hara in '86. There's another famous result on this cohomology by many people, Miller, Mumford, and Morita, for instance. And eventually it was proven by Madsen and Weiss in 2007 that the stable cohomology, so that means the cohomology in very low dimensions. So if the k is small and the g is relatively large, then we know how the cohomology looks like. And it's generated by a set of forms, these kappa classes, these kappa forms. So the kappa I is some form of degree 2i. And the statement of the seminal theorem is that the stable cohomology is completely generated by these stable classes, these kappa classes, up to degree k smaller than 2/3 g minus 1. So we have this polynomial algebra that tells us about the cohomology in low degree. So here's a picture of this cohomology then. So the dotted line is the maximal degree, 4g minus 5. And above that, the cohomology vanishes. And unfortunately, you can barely see the difference between these two regions here, at least in this room. But there's a difference. So here's the bulk of the cohomology where we actually have cohomology. Yes, you want? No, this is just normal. It's not compactly supported cohomology. It's just a normal cohomology. Yeah. You can also think about it. You can also dualize to singular homology, but then the forms are not necessarily compactly supported. No. The forms, yes, I think so. So these are just finite dimensional vector spaces. They are not normalizable. Right, they would have to pair non-trivially. So yeah, I take that back. That's true. Thanks. Yeah, so it's not trivial to pair actually these differential forms that you have. So that would give you like lots of information on the space. So this blue region here is the stable cohomology that has been proven by Madsen and Weiss to be exactly there. So this is slope 2/3g. So there in this regime we know everything, and here we know barely nothing at all in this big wedge, big area here. And the reason why this is especially puzzling is because you can look into the Euler characteristic of the space. So the Euler characteristic is just the alternating sum over the dimensions of all the cohomology groups. And this Euler characteristic, it has been computed and estimated by Hara and Sergier also in '86. And they've proven that the Euler characteristic behaves like a constant times some alternating sign, so g plus 1 to the power, minus 1 to the power of g plus 1. And then some term that grows super exponentially. So it grows like c times g to the power of 2g minus 3/2. And that grows like a squared factorial. So it grows doubly factorial for g to infinity. And of course, trivially, because it's the alternating sum, we can just estimate the sum from below by the magnitude of this Euler characteristic. And this immediately proves that the total amount of cohomology in this space grows super exponentially with g. It grows at least as fast as doubly exponentially with g, doubly factorially with g, sorry. Can we find this doubly exponential, doubly factorial growth rate in the stable cohomology? And the answer is obviously not. So if you look into the dimensions of these spaces that are just generated by these kappa classes, we can estimate their number, and the number is just the partition number. So the number of polynomials of degree, the dimension of the space of polynomials of degree 2k that you can build out of these kappa forms, it's exactly the number of partitions of k. And the number of partitions has been estimated very famously by Hari and Ramanujan, who in the early 20th century, who figured out that it's bounded by some constant to the power of square root of k. So the amount of stable cohomology, it grows less than exponentially. So in summary, we know that the total amount of cohomology grows doubly factorially, but the stable cohomology only grows less than exponentially. And this is what is called this dark matter problem of the modular space of curves. So we know that there's lots of stuff happening in this area above the stable, in this unstable area, but we don't know really where it comes from. So this is a question mark. So this is the dark matter problem of MG. Yeah, so this is small, the stable cohomology. And there are also some explicit computations, and because this is like pretty analogous to the situation in high energy physics, where people can sort of, by throwing the computational kitchen sink at such a problem, go a bit farther and a bit farther. So here the computations are also very complicated, and you can actually compute this cohomology ring by just using big computations. People have done so up to genus 4. And these are these people. And what comes out are exactly 4 classes that are known of the super exponential growth rate. So yeah, so the picture is not very satisfying, and each of these classes also gives like interesting information on so gives an interesting invariant of the space. So cohomology always gives interesting invariants. So this is everything that has been known before 2021. And everything that came on top of that, so essentially everything that has been known, everything that came on top of that later is due to this tropical geometric variant of the modular space of curves. So this is the next part of the talk. This is this tropical hunt for classes in the modular space of curves. And it's an attempt to explain like these huge amounts of classes in the modular space of curves using a tropicalization of the modular space. So what is tropical geometry? Tropical geometry is a drastic degeneration technique in algebraic geometry, mainly, and it's in which the limiting object is entirely combinatorial. And I have to say that this is also just a slogan, so it's not really a concrete recipe. And I also have that from a review on this by Melody Chan. So, but this is what to keep in mind. And of course, from the perspective of physics, the intuition is more that we want to go into like some singular limit and understand the singular limit completely combinatorially. So here the modular space of tropical curves is the next main player, therefore. It's a certain tropicalization of the modular space of curves. And in fact, it's also just a modular space of metric graphs. And there are some technical details. So actually, it's the modular space of stable metric graphs. But I'm going to explain like what this MG trop is now in the next part of the talk. So in contrast to surfaces in the beginning for the modular space of curves, we are now talking about graphs. And this MG trop is the modular space of metric graphs. So we assign a metric to each graph. The metric on a graph is just a dedicated, it's just given a length to each edge. And we are interested in this modular space of graphs up to isometries. So also graph has automorphisms, and we only differentiate between those that actually have a genuinely different metric. And that space originally goes back to Kaller and Vogtmann from 86 as well. There's a physics analogy here as well. So the modular space of curves is like 2D quantum gravity, and the modular space of tropical curves in a way is like 1D quantum gravity. So where we really just have one-dimensional objects and we somehow glue them together. So here's a picture of the genus 2 tropical modular space. Here the objects are graphs. So here are 2 examples. It's the theta graph here and here the handlebar graph. And just as in the modular space of curves, we can also move around in the space. So here, for instance, I can shrink one of the edges to a point, but in contrast to the modular space situation, to the modular space of curve situation, we can now go to the boundary. So in MG trop, we actually have a compact space, and this is important for this construction actually. That here in this topical modular space we have a compact space, so we talk about stable graphs. So also we have this symmetry, so we mod out isometry. So actually this graph here, which is sort of slightly left of the barycenter of this face of the simplex, is copied 6 times by the inherent S3 symmetry of the theta graph. So you imagine that there's a S3 symmetry that just permutes these edges acting on it, and in the modular space that reflects itself as a S3 symmetry that just rotates this triangle. So all these red points are identified. We can then have like multiple different examples of such metric graphs in this modular space. And there's one extra thing that extra interesting thing that happens, namely that there are kind of UV divergences in this modular space as well. So we can shrink a loop to a point, a tadpole to a point. And so if you have a point here close where we're sort of about to shrink one of these tadpoles to a point, then we would run into a problem, because if we just shrink it to a point and do nothing else, then we change the genus of the graph. But what we have to do is we have to add like a little reminder that this vertex that we have encountered, it actually came from a loop that we shrunk to a point before. And we can also iterate this. So this is a stable graph now with two mark points. And for the experts, so this MG trop is vaguely analogous actually to the Deligne-Mumford compactification of the modular space of curves. It's not, but this is, the tropicalization sort of wants to also make it compact. All right, so let's go back to MG and let me give you some intuition, like where this or how this tropicalization of MG works. So here's again the picture from the beginning of MG with all these surfaces. And what we want to now do is we want to describe we want to extract only the singular behavior of these kind of curves and thereby get a map to this tropicalized modular space. And the trick is to identify these most singular cases, so these cases where there's like a long tube. And we do this by first defining a cutoff. So we cut out some of the boundary of the space. So so we want to have like a singular curve or an almost singular curve. So what we do is we define an epsilon, some number, which is only which has to be larger than 0. And then we look into all geodesics on our surface that have a length that is strictly smaller than epsilon. So we only look into geodesics that are small. So here, for instance, in this genus 2 surface, we might imagine that we find these two geodesics, L1 and L2. And it's actually a theorem that if epsilon is small enough, then these geodesics, they never intersect. So they're always disjoint. So the next step, what we do is we cut the surface along these short geodesics. So we just cut it along them, but we remember sort of a manual how we are supposed to glue it back together if you want to. So these are these pink edges here. Then in the next step, we take like the connected components that we got, and we map we write a vertex for each connected component of the surface. So for instance, in this example, we take this vertex here, which has 3 legs, and we take 3 legs because the surface that we started with, it has 3 boundary components. So for each boundary component of the resulting surface, we make one leg. And here we do the same. So this part of the surface has only one boundary component, but it has also genus 1. So for the vertex we associate to it, we write this, we write a 1 to the graph. So this is also called stable graphs, this construction that I'm just explaining here. And the next step, we just add these edges. So we still remember the way we are supposed to glue the boundaries together. So we add some edges that come from this gluing data. And now we have a graph. So we are almost there in the modular space of tropical curves. We only still need edge lengths for our edges. And the edge lengths, they come from the lengths of the geodesics. And you've also seen this during the workshop a lot. It's a common theme in tropical geometry to always take the log. So we take the log of the length of the geodesic over epsilon. And that's always a strictly positive number. So we get some positive number here for our metric graph. Okay, so this defines a map between the modular space of curves and the modular space of tropical curves. And it depends on this parameter epsilon. And this was constructed by Abramovich, Caporaso, Payne, and also by Chan-Galatius-Payne, who used this construction. What I want to emphasize here is that if you look into the modular space M2, the important feature here is that with this cutoff epsilon, we essentially focus on the boundary of this modular space. So what we do, we cut out a part with some small geodesic. So we take only surfaces into account that have some small geodesic. So we can imagine like cutting out like an epsilon piece of the modular space and looking at the surfaces that fall into this boundary. And these are then described by this tropicalization. And you can also already see that if you understand the shape of the boundary, so understanding the shape of the boundary also gives you information on the topology of the original space. So because of course the boundary has to surround like the holes of the space. All right. So this means that mg-trop captures information on the boundary and also gives therefore information on the topology of mg. And I'm not going to explain in detail how this works. It has something to do with a very beautiful story by Deline on mixed Hodge structures. We also heard about this during the conference, but I'm not going to explain it. The first result where people made this effective in this case came namely in 21, where Chan-Galatius and Payne, they proved that the homology of this tropical modular space injects into the cohomology of mg. So there's an injective map from the homology of mg-trop into the cohomology of mg. And there are some complicated shifts here of degree. So there's also an application of Poincaré duality hiding here. So I'm not going to explain this in detail. So yeah, but the k-1 chains or classes in homology, they inject into 6g-6 k dimensional cohomology. Right. So that's why the homology of mg-trop is interesting. And here's now some results on this homology. The motor of many of these results is that the homology of mg-trop, it can be described completely by graphs. And in fact, it can be computed completely by an object which is called the commutative graph complex. And it was invented by Kontsevich in '94. So this graph complex is a very combinatorial object. So it's a complex where the chains are all graphs. So GGK is a vector space that is generated by graphs of genus G with k edges, and the boundary maps, so to passing like from a graph with k edges to a graph with k-1 edges, just contracts the the edges in all possible ways. And Chan-Galatius-Payne proved that the cohomology, the homology of MG trop is completely computed by this graph complex. This graph complex also has many other applications, for instance, in deformation quantization, for knot invariance, there's also related constructions on configuration spaces. It also has important applications for out Fn. This is something that I very much like, and to integrability. But here, the most relevant results is that there's sort of a stabilization implied by the homology of this graph complex on MG trop. So that means that for small k and large enough g, the homology vanishes. So there are no small dimensional holes in this in MG trop. So for k is smaller than 2g minus 1. The next important result is that there's a funny thing that happens if you put all the homology classes of MG trop in degree 2g minus 1 together in a single space. You find that these homology classes actually form a Lie algebra, and this Lie algebra is a very mysterious object called the Grothendieck-Teichmüller Lie algebra, and it's actually also closely related to objects that we heard about during this week, namely these KZ equations and associators on this, but and multiple zeta values. But yeah, it's still not a very understood object. There's one effective theorem on this Grothendieck-Teichmüller Lie algebra by Francis Brown, who was also here during the week, and that is essentially that there is a free Lie algebra hiding in this Grothendieck-Teichmüller Lie algebra. And this free Lie algebra is generated by essentially the odd zeta values. So the sigmas correspond to sort of zeta values. And as a consequence of this, so this free Lie algebra, it has quite a high number of generators. So because you can always form Lie brackets of different generators, so so there's a large number of generators in this Lie algebra. So we also know that there's lots of homology in the space due to this injection of this Lie algebra. In fact, the dimension of this Lie algebra, it grows at least exponentially with G, and therefore there are also exponentially many classes in this diagonal of MG trop. And there are also some explicit computations by Dorvanathan, Bren McKay, and Wilwacher of classes, and because the computation, the complexity is much lower for this commutative graph complex, you can go much further with computations. All right, so here's a picture of MG trop of the homology. Yeah, so this blue wedge here again is the stable cohomology, which is homology that just vanishes. Then the pink line is this mysterious Grothendieck-Teichmüller Lie algebra that lives there. But we know there's exponential amounts of homology hiding in this line. And then these orange classes here are some explicit computations that actually go up to loop order 10. So it goes quite far in this case. What other things happen in this pink wedge, nobody really knows. So you can compute explicitly up to loop order 10, but then yeah, then it's unknown. Okay. So recall that Chan-Galatius-Payne, they used the structure of the boundary that can be identified with MG trop to say something about the cohomology of MG. So they found this injection. And so remember that we had this sort of not so filled picture of MG in the beginning. That was sort of the status quo before 21. And with the Chan-Galatius-Payne result, we now have the homology of MG trop living inside the cohomology of the modular space of curves. And we have sort of a nice infinite exponentially growing sequence of classes here on this upper diagonal, which is actually the topmost degree. So they all live in the topmost degree. And then we have like these 5 more individual classes that are in relatively high genus from the perspective of computations on the modular space of curves itself. So that's the first progress in this dark matter problem of the modular space of curves. So suddenly there's like a new source of classes. And this new source also immediately overshadows the former stable cohomology of the modular space of curves, because this is only growing sub-exponentially. So it's like the new main source of information on the topology of the modular space of curves. Okay, so the question is now, and this is now where so this was all review. So this is now the part where some new results come up. The question is now obviously, can the dark matter problem be solved by the modular space of topical curves? And yeah, so can this injection explain like this large growth rate of the cohomology by Hara and Zaghi? And so this is also work in progress, but the paper is going to appear very soon. And the idea here is to estimate the amount of homology in MG trop using Euler characteristics, just like in the Hara-Zaghi formula. So we want to compute the Euler characteristic of MG trop. For MG trop, the Euler characteristic is again just the alternating sum over the Betti numbers. So we just have to compute the dimensions of all the homology groups. But computing the dimension of the homology groups is very hard. But fortunately, with the Euler characteristic, so this is the main feature of the Euler characteristic, is that we can take any chain complex that computes the homology to compute the Euler characteristic. So we can just, instead of the homology groups, we can just take the chains from Conceivit's chain complex to calculate this Euler characteristic. This is exactly what you have to do, of course. So we can reduce this Euler characteristic computations by using Conceivit's graph complex to a pure graph counting problem. And what we have to do here is to just take the alternating sum of all graphs with G loops and K edges, and we have to alternate over the number of edges. Okay, it's the number of edges. And there's some technical additions to that. So actually we have to exclude some graphs, but yeah, this is just technicalities essentially. We need to compute in essence like this alternating sum. We take an alternating sign with all graphs of genus G with K edges. And of course, we can just rewrite this as a sum over all G loop graphs. So we take all graphs with G loop G, all graphs G with G loops. So that's a bit complicated to read, I'm sorry. And we alternate then, we take a minus sign if it has an odd number of edges and a plus sign if it has an even number of edges. This is a bit complicated to evaluate such sums because we have to effectively here take all the isomorphism classes of graphs. But if you're a quantum field theorist, you know that there's a much simpler thing to do. Namely, we can just use a toy model where we sum over all G loop graphs, but we weight each graph with 1 over its automorphism group with the symmetry factor. So this is something that can be evaluated easily via actually a zero-dimensional quantum field theory. So this is a very easy problem. So just here to illustrate this point, so this is a toy version of the problem. So at genus 2, we have this theta graph, and we take -1 to the power 3, and it has symmetry factor 12. So the automorphism group of this graph has order 12. So we take -1 to the power 3 over 12. And then we take the double tadpole graph, which is -1 squared over 8. And here the handlebar graph, that is -1⁻³ /8. And so you get this very famous number that always appears in this context magically, -1/12. And yeah, you can also do the same for genus 3 and so on and so forth. So how do we, so if you, yeah, of course you have to be a quantum field theorist to know that, but you just package this, this expression here into a generating function. So we sum over all graphs, we weight each graph by its symmetry factor, we alternate in the number of edges, and we introduce a parameter to account for the number of loops. And then everyone who ever did like quantum field theory knows that we can just write this as the log of some path integral. So this is just a zero-dimensional path integral, and the action here, it's just crafted in the way to generate these -1s as Feynman rules, so to say. And we only want to have like graphs with vertex degree larger than 3. So we only take interactions into account with vertex degree larger than 3. And yeah, so this part here can be solved explicitly, and it generates some Bernoulli numbers. And in fact, what you get, these Bernoulli numbers, also have a meaning in this modular space of tropical curves, and it computes their virtual Euler characteristic. So there's an orbifold type of Euler characteristic that you can associate to such spaces. So it's a rational number. So I had this example here before. So -1/12 is of course not a proper Euler characteristic because it is a rational number. But there's a notion in which you can actually make very good sense of these rational numbers as Euler characteristic. And this is the orbifold Euler characteristic. All right, but we actually want the true numbers, the actual Euler characteristic. And you can also do that. And this is one of the main results of the new upcoming paper, is that you can do that by doing like an infinite field zero-dimensional QFT. So you can define like a function. So I know that people here are not scared of complicated expressions, so I'm showing it. So you have infinitely many fields that are indexed here by xk. And the action is sort of a coupled expression that couples together all these infinitely many fields. And this generates also correction terms that account for this, that remove again these these symmetry factors, these rational numbers. So they make the rational numbers again into integers, such that we actually count the proper number of these kind of graphs, the proper alternating sums of these graphs. XKL, this is like x of k times L. So it's, yeah, sorry, there's a dot here, right? Yeah. So it mixes all these kind of fields, but because in this exponential way, they are all mixed together somehow. So it's a bit, it's not, yeah. Yeah, and if you just compute this, this zero-dimensional or still zero-dimensional QFT, you get a generating function for these Euler characteristics of MD trop. And you have to actually use the plothistic logarithm here to squeeze it out again, these numbers. Okay, yeah, so this actually can be solved explicitly. This is pretty cool about this. There's actually like it looks more complicated, but actually it's simpler to handle. This is an explicit solution of this infinite dimensional integral, which involves Bernoulli numbers and yeah, also some logarithmic connections. So this gives you an easier way to actually get a handle on these numbers, on these Euler characteristics of MG trop. Yeah, so what's important now for the story that I was telling you before is the asymptotic behavior of this Euler characteristic. So the asymptotic behavior goes as follows. So for large G, and yeah, and what I also of course want to mention, so you use a kind of a semi-classical analysis of these expressions to get this asymptotic behavior. So this is a large large coupling expansion, so to say. And yeah, so you can call it semi-classical analysis, or yes?
Does accounting for the symmetry factor?
Yes. Yes, that's funny, but the reason for this is that there's a cancellation that makes it, if you include so I mentioned before that in this toy model, where you just weight each graph by one over its automorphism group, you get Bernoulli numbers. And every second Bernoulli numbers vanishes. So these virtual Euler characteristics, they just vanish for odd G. And so you get nothing, and the correction terms are just everything. But you're right that for even G, this term here actually comes just from the Bernoulli numbers that pop up. So there's no the correction terms are negligible. But for odd G, the correction terms are pretty funny. So they look like this. So we have a heavily oscillating function. So this is a sine of which includes a square root of pi times G. And yeah, so this will be a rapidly oscillating function for large G. And then we have like something which goes sub-exponentially, so with some constants times the square root of to the power of the square root of G. And then there's still here some term that grows effectively half factorial. So it's like G to the power of G over 2 for odd G. So it's not a full factorial growth rate in this case. So it follows from this that there's a constant C such that for large G, for sufficiently large G, we have this Euler characteristic bounded from below by something that grows factorially and by something that grows half factorially. And what's quite funny about this is that to prove this, you actually need, so yeah, so because some people are also interested in number theory, you actually need information, like you have to estimate how small the sine can get for a large G. And to do this, you have to know how close like the square root of pi times G can get to a multiple of pi. And if you resolve the exercise, you actually need to know like how irrational pi is. So you can really go and look into these known irrationality measures of pi, and that gives you the nice bound here. So if it would be any transcendental constant, it would be hopeless to prove something like this. But luckily, it's just pi, and there everything is known. So yeah, so that's sort of one part of the story. There's another part of the story. So I mentioned before that I quickly want to mention that there's a related computation for the group of outer automorphisms of the free group and the modular space of pure graphs. I was telling you that this modular space of tropical curves is actually compact, but there's another version of this modular space of graphs which is non-compact, and where we don't have these vertex decorations, and it's also a very interesting space. So I have here a little table. So because the situation is a bit confusing, some of the objects here are named, so I have symbols for them in this talk. Some of them don't have a name. So we have here the world of surfaces and complex curves, and here the world of graphs and tropical curves. And there's like open modular space versions in both worlds. So this is MG, the modular space of curves. And here we have this modular space of pure graphs. But if it wasn't for this talk, I would have just called it the modular space of graphs, because it's kind of the more natural object in this perspective. Then there's a compactification of these modular spaces, which is the Deligne-Mumford compactification in the modular space of curve case, and MG-trop in the graph case. The initial modular spaces, they are also classifying spaces for certain groups. And this is also why these objects are very interesting. So MG is a classifying space for the mapping class group of an orientable surface of genus G. And similarly, this modular space of graphs is a classifying space for out FG, for the group of auto-automorphisms of the free group. But also there are different upstairs spaces. So these are fine modular spaces where we don't mod out by this. So these are modular spaces. These are spaces that are actually contractible. So Teichmüller space in the case of the modular space of curves, there's an action of the mapping class group on Teichmüller space. And here the analogon is outer space in the modular space of graphs case. And I'm just mentioning this because there's been a lot of talk about outer space during this week. So this is the complete picture with all these relations. And this the relation that I'm talking about today is, of course, this connection between MG and MG trop. But this is kind of, it fits only diagonal in this whole picture. So there's some kind of clash of notations here, actually. All right, so going back to this tropical, so out FG and this modular space of pure graphs, there's a related story, and out FG is also a very interesting group. So with my fantastic collaborator, Karen Vogtmann, we looked into this modular space earlier this year, and we proved that the Euler characteristic of this group out of G, which can be identified with the Euler characteristic of this modular space of pure curves, it also behaves, it grows super exponentially, but here with this G over E to the power of G, and it's modulated by a G times log G square behavior for large G. So this is from earlier this year, and this uses related methods. Related methods to this theorem that I mentioned earlier on this asymptotic behavior of the Euler characteristic, of course. So back to MG trop and MG. Here's now again this picture of MG trop with this pink wedge, which there's no explanation for. And the new theorem, the upcoming theorem, says that there's actually also a dark matter problem here. So there's lots of stuff in this pink wedge which we don't understand, and the amount of this stuff grows rapidly with G, super exponentially with G. And this this pink line, it does not really explain it because it only grows exponentially. Okay, so we can also just map this back to the modular space of curves. There's a bit of a more precise statement that I didn't really talk about that has to do with this mixed Hodge structure on the cohomology of MG. In fact, the Chan-Galatius-Payne injection, it's an isomorphism if you restrict to the top weight part of the mixed Hodge structure of MG. So what this theorem says is that the dimension in the top weight, so the top weight is 6G minus 6, of the cohomology of the total cohomology in this top weight, it grows more than exponentially with these kind of rates depending on G. So translated to pictures, that just means essentially, I mean, it means a bit more, but if you look again in this red wedge that is identified inside the cohomology of MG, then we now know that in this red wedge we have super exponential amounts of cohomology identified. So there's super exponential amounts of cohomology that live in this red wedge. And yeah, so now back to the initial dark matter problem of the modular space of curves. Here we now can compare it. So the total amount of cohomology due to the Hara-Zagier result, it grows like G to the power of 2G, at least, like G to the power of 2G. But in this red wedge, we only have identified G to the power of G or G to the power of G half much homology or cohomology. So the dark matter problem is only partially solved in this case. So there's also in this, actually, so making this a bit more precise means that there's actually also lots of cohomology here living in the rest of this space. So yeah, in summary, so this is the old result by Harazage on chi and G. The new result, upcoming result, says is something similar on the modular space of topical curves, and it also grows super exponentially, but less than the cohomology, than the bound by Harazage. All right, so the conclusion is there's still lots of unexplained dark matter in the modular space of curves. Thank you.
Any questions for Mishi?
In the last slide, does any of these say anything about torsions when you work over Z coefficients? Maybe the picture before.
No, nothing on torsion.
So we don't know whether they grow or shrink.
No. You could try to say something about the torsion by comparing it with the virtual Euler characteristic. So the virtual one gives you some information on the torsion, but very little. So that would be, yeah, maybe that would be feasible.
Francis was telling us about a slightly different complex where you essentially blow up every simplex by the subgraphs.
Yes.
Does that define a homology that injects somehow on the cohomology that you were telling us about?
Yeah, that would be, so what Francis was talking about is like the exactly the same story, but applied again to the tropical curves. So that's, I had this picture of the modular space of graphs. Yeah. So what you want to do is you want to cut out you want to do the same which I illustrated on the modular space of curves again to the modular space of topical curves. So you cut out some of the boundary and you describe, so you blow up the boundary and you describe the homology of the boundary then again. So that's what my friends did. And you can then learn again something about the cohomology of this space. So it's a bit of a technique to learn something about.
Yeah, in this new multi-component zero-dimensional path integral, does it resemble any of the known large N limits? Like say when you go to the large number of components?
I don't know. No, it's just yeah, maybe we can study this in this. Yeah, I didn't think about this. Sorry. No, I don't know if it's, but it would be interesting to somehow, yeah, get some symmetry, some n-fold symmetry in there, and then study the Latin limit.
For components, how does it grow with the G, like the number of components you need?
The number of components of the graph, so the
zero-dimensional field.
Yeah, it goes linearly. So you have to take like 6G minus 6 and to compute up to G. So you can cut it off if you only have to have, if you only want to do a finite order computation. But yeah, for the asymptotic, of course, you need the full thing, but then you have to estimate the cutoffs. So asymptotically, also not everything contributes. So yeah.
Maybe in the large G limit, you get some kind of large N type structure.
Yeah, that could be right.
Sorry, is the homology of this pure graphs moduli space related to anything on the left-hand side in terms of MG and MG bar?
Yeah, that would be very interesting to. So there are like some ideas. So there's here. So the homology of this space. Yeah, so very little is known about that. There's a conjecture by Morita that there is an infinite family of classes here, but it's only a conjecture. So they are cycles. They are the Morita cycles. But yeah, so there's no known relation with either this one or this one. So yeah, one might naively expect that one can maybe cross over somehow, but nothing like this. No.
Be clear, this is coming instead of the Kontsevich commutative graph complex. For the moduli space of pure graphs, you're using a graph complex that doesn't keep track of jitters or something.
No, you can also define, actually Kontsevich also wrote down a graph complex that computes the homology of this pure graph complex, pure modular space of pure graphs, and it's the Lie graph complex. So, but it's more complicated, much more complicated than this commutative graph complex. Yeah.
Can you give a little bit of intuition for your action?
Yes.
Way of this X sub KL. What does that ordering mean in
yeah, it's like yeah, one way to think about it. So yeah, there are multiple ways to think about it. So what you have to do is you have to counter the effect of these 1 over out factors, and the trick is then to just say, okay, let's just add new fields that are sort of responsible for generating cycles of size 2, so automorphisms of size 2, size 3, and so on. And of course, they can all interact. So so what this generates here is like all kinds of cycles, or each higher X field stands not for a single vertex or a single half edge of your graph, but a whole cycle of graph edges that are permuted by some permutation. And if you do the combinatorics, then you find that these behave essentially also like half edges of a graph. So you can pair like cycles only transversely. There's like then multiple ways to do that. So you can cross some edges, and this is how you get this 1 over k factor here, for instance. Yeah, so this is roughly the idea, that you want to somehow fudge yourself back into like only generating the total amount of graphs without any symmetry factors, error terms. But they're also, so what's hiding in here is also all the signs. So and there's like massive cancellation. So they all canceled already, because I only wrote down like the most compact expression. So if you want to do something slightly different, such that just counting the total number of graphs without the alternating signs, the expression becomes much more complicated. So a lot of the intuition that goes like into the beginning into it is already gone, I'd say. So it's magically simplifies to this impression. So I just showed you one of the end results here.
Yeah, sure. I don't know who was first. Yeah, but
yeah. So just a curiosity. So is there a story, or would it be a very different story for punctured surfaces, for punctured curves?
No, it's not much more complicated. Yeah. So with punctured surfaces, so if you can define a surface with punctures, and if you then tropicalize in the modular space of graphs, you get graphs with legs. So yeah, so this is the obvious thing kind of works. No, it's actually easier in a way. Especially one puncture is very helpful. Right.
I'm not hallucinating if I see something like in your tropicalization, like the field theory limit of string that gives you final graphs.
Yeah, I mean, this would be fantastic to have like some real physical implementation. Yeah, I don't know. Yeah, I am not an expert on this, but yeah, it would be fantastic. Right. Yeah. If somebody has an idea on how to actually put so I really like this modular space of tropical curves, because I think about it also as a natural space for quantum field theories. But yeah, so this modular space of curves is of course very natural in string theory. So yeah, so somehow maybe use like, yeah, known string theory results in the relation of the degeneration of the strings to quantum field theory would be somehow possible, but I don't know.
What you have there doesn't look like a convergent integral. Does it need a minus sign?
Yeah, that's right. So it needs a minus. It needs actually what I want to integrate here is for each x over the imaginary axis. So that's and this actually is also responsible for the minus signs, because this way it also looks completely positive. So there's no cancellation. So I don't so you don't really see how this how all these minus signs pop up. But you need to mind
The -1 minus xk subtracts the first two terms in a Taylor series expansion of L is 1.
Yes. Yes. Yeah. So these terms are actually playing a role. Right. Yeah.
Is there open version of this math matter problem? So is there a counting fat graphs rather than ordinary graph?
Do you want to? Are you trying? Do you want to make the joke of, is there a dark matter problem in outer space? I mean, no, not in this outer space. So yeah, this outer space is contractible, like just like Teichmüller space. So there's no interesting homology here. But in this space, in the quotient, in the modular space of pure graphs, there's a dark matter problem as well. And it's even more severe. This is what I proved with Karen. So because the order characteristic here grows so much, we know that there's lots of homology. And yeah.
That moduli space is or isn't related to a graph complex about fat graphs?
That's the Z graph complex. Yeah. So this is also related to fat graphs. But yeah, no, the actual thing that you want to compute here is the B graph complex.
Any other questions for Mishi? All right, if not, let's thank him again.